So in this video, what we are going to work on is is logistic regression study. So basically, we have a heart disease data set, and it contains information about different patients that might have a heart disease or not. So that's what our data set looks like. We have a history of patient, and based on that, we also have either they have a heart attack or heart disease or not. Now, to do so, what we're going to use is logistic regression. Logistic regression is a machine learning model that basically helps us to predict categorical columns. Like if we are trying to predict some categories, we go with logistic regression. In previous session, we talked about linear regression. Linear regression works only when we have numeric columns. When we have categorical columns, we go with some classifier, and logistic regression is basically a classifier. Now, as we talked earlier, that whenever we're working on something, we must have the domain knowledge, like what we are really dealing with here. Now, in this case study, we are going to deal with heart disease dataset, and we have different columns. And first, we need to know that what they represent. We have age column that represent the age of patient, gender. CP basically is a column in dataset that basically represent chest pain type. It contains chest pain type. It contains 0, 1, 2, 3 different values that represent different types of chest pains, right? And in gender, if we have a value of 1, it means male. If it's 0, it means female. So basically, this is something that we call data description. And whenever we are working on some kind of data set, you must have data description, like what they they basically means. We have resting blood pressure, cholesterol levels, fasting blood sugar, and different medical terms, right? So basically, whenever you go in some hospital, they take a history, and based on that, they consult you to the doctor, right? So basically, this is what we call history. Now, there is a variable in the data set represent target. So basically, it represents that either they are diagnosed with heart disease or not. So if it's represented with 1, it means they have, and it's not, then it's represented with 0. So basically, that's the data of patients that come to a medical hospital and they collected it, right? So basically, we have data set related to different 300 patients. Now, what we are trying to do here, we are trying to create a model that predicts that. Now, in our data set, the target column is basically that diagnosed by doctor that they actually have the problem, right? But what we want to do is we want to use this information to predict. So whenever a next patient come in our hospital, we get all these columns, all these values related to that particular patient, and based on that, we predict the chances of having a heart disease. Now, first we need to understand what logistic regression is. Now, logistic regression is basically the algorithm that is going to be used to predict that, right? Now, we see that in linear regression, we have equation like y is equal to beta naught plus beta 1 x1, beta 2 x2. But in logistic regression, we have this equation. Now, why we have this equation? Because we are trying to predict either 0 or 1, basically two categories. Okay. And based on two categories, what we need to do is, now we cannot predict actually it's going to either 1 or 0. So what we are going to do is we are going to predict a probability value that these are the chances of having a value 0, or these are the chances of having a value 1. Now this is the equation, and if we want to compare it with our previous equation, we see that both of them looks quite similar. Let me open the other one. So that was the equation of linear regression. Okay, and we have beta naught, beta 1 x1, beta 2 x2, and here we have y. But in this equation, we have p of y. So basically, we're trying to predict the probability of having something, like having 0 or having 1. Okay, and on the right side, we do have this expression right here, but it's in 1 divided by 1 plus exponential format, right? Why we have something like that, I will discuss it when we go a little bit further. Now, in linear regression, we have something like that, right? We had equation, we find intercept, we find beta 1 that mimic the line on it. But the main problem with linear regression is it can go on and on to any value. Like we have related to 5 for 452, but we need only two values, 0 and 1. So we basically use this formula to map the values between 0 and 1. And how it works, I will show you. Now this formula, 1 divided by 1 plus e minus this, that's also called sigmoid function. Okay. And it maps the values between 1 and 0. Now, how does it do that? Let's talk about that. No matter what value you provide in this formula, your values will be always be between 0 and 1. Okay. And we will talk about it in different examples here. Like in this particular example, we're talking about classifying emails. So in every whatever email service you're using, like Gmail or Yahoo Mail, you have a spam folder where emails go that these emails are spam and they should not be show up in notification, right? So what we are going to do is we have a data set, three different points, and we will find the optimum beta naught and beta 1 that will create a line that follows that. Again, we have an intercept that if we just make it 0 and move around with the intercept, that's going to be the same thing like we have in linear regression, right? Now, in case of the main purpose of using this 1 divided by 1 plus exponential is basically to get the shape of the line that fit around between 0 and 1, right? Like if we see something here, so basically when we generate the weights or the coefficients beta naught beta 1, we get values that basically try to create this particular curve. Now the question is why do we want to create a curve or an S-shaped curve like this? Basically we are trying to predict either we're going to get a 0 value or 1 value, right? And the above point basically represent 1 and this point basically represent 0. So whenever we pass all the values, independent variables through this formula, we will get points between 0 and 1, right? And in these points, we define a threshold value. Threshold value is basically that dotted line. So what it does, it will basically classify the above points into one category and the lower end points into 0 category. And it's adjustable, so we can adjust it as we want, but we need an optimum threshold to get the maximum accuracy. Accuracy means basically let's say there are 10 heart disease patients and our model is predicting how much our model is going to predict from them. Like if our model is predicting all 10 of them, it means we have 100% accuracy here. Okay, now there's a little bit of comparison between linear regression and logistic regression. We cannot get the values between 0 and 1. That's why we need something like logistic regression to classification problem, right? This is the formula. This is also known as sigmoid function. Here Z is basically the linear combinations like beta naught, beta 1, x1, beta 2, x2. Now here we have probability of the category is equal to this. If we want coefficients in the proper format like linear regression, then we will have on this side of equation we will get something like this, ln of p divided by 1 minus p. Why? Because we need to implement log on it to keep the coefficients out of the equation. Now in linear regression we can interpret the coefficients, right? We know that the coefficient is significant. If it's significant, it has this coefficient, and this coefficient basically have this particular meaning. But in logistic regression we cannot use them like that. We cannot interpret them like that. What we need is odd ratios. Now, what is odd ratio? Odd ratio basically whatever the coefficient we get from logistic regression, whatever the value we have here in the equation for beta naught, beta 1, we will take exponential of them and this will work as odd ratio. Why we calculate odd ratios? Because we cannot interpret the coefficients as it is. We can only interpret the odd ratios from the equation. Now, if odd ratio is equal to 1, it means there is no association between these two. If it's greater than 1, we have positive association, and if it's less than 1, we have negative association. Do you have any question till now? No. Okay. So what we are doing here is, let's get back to our problem. We have all this previous information and we are going to use it to create our application, our own application that basically helps us to predict the heart disease, right? Again, we know that what we need to do is whenever we train a model, we split the data set into training and testing, right? We also know that all these columns are basically our x columns are independent variables, and this is our dependent variable. Now let's move back to our code. Code is going to be the similar. We import some packages. We will use sklearn. From sklearn, we will use train test split, basically a function that helps us to split the data. Also, we are going to export logistic regression function from sklearn standard scalar to scalar our independent variables. And now we are going to have some matrix like accuracy score, confusion matrix, classification report. So basically, it tells us about how good our model is. We will discuss them when we go to this step. Okay. Now we have a data set in CSV file. So if we want to load it in Python, all we need to do is just use a function from pandas read CSV, and we will see that it's loaded, right? Now we are since in Google Colab, so if you want to use this data set, you have to drag the data set in this particular section. I already did that. That's why we are seeing a dataset.csv here. But if you are in Jupyter Notebook, you should have the data file in your working directory. Now dataset is loaded, and we use the info command to see if there are any missing values. There are no missing values. Data.describe. So basically here with data name is df, so that's why df.describe. Now here we are trying to check that how many categories we have in our target variable, like 0 and 1, and how many we have in 0 and how many we got in 1. So there are 165 in 1. So there are 165 patients and 138 that don't have heart disease. After that, we created some different plots here, like a bar plot and a pie plot. Again, we discussed that we can create that from the matplotlib package, and we're using that right now. We discussed the styling here. The new thing here is that instead of using the function plot separately, that like plt.plot, we are using directly on our target column. So basically, we use the data target column from data, and we get the count values, and on that we put the plot, and we specified that it's going to be a bar plot, and we specified the color scheme here. If you want some different colors like red and blue, you can just specify here. Again, you can also, for different kind of plot, you can also specify here. Like in the next session, we just created pie plot. The rest of the code is same. Now we are going to go through the data processing step, where we check for the missing values, handle any kind of data quality issue, prepare features and target columns. So basically what we are going to do is we check missing values. They are not there, so we don't need to worry about that. After that, we will split our data set into independent and dependent feature, right? Now here we are using df.drop. So basically we're dropping the target column here from here because we are creating a data set for independent columns. And y is going to be the target column here. So basically, as we discussed earlier, that this is going to be independent columns are x, and this is going to be y. X.shape basically represent how many values, how many rows we have in the x columns and in y columns. Like if we go here in x columns, we have 303 rows and 13 columns, and here we have only single column that's our target column. Now this is the separation between independent and dependent columns. Now we are going to separate them based on the training and testing set. Again, for training and testing set, we will use test train split function. We already discussed that, so there's nothing new here. And based on that, we will create training and testing sets. So this will split the data set into x train, x test, y train, y test. The new thing here is that we are specifying x for independent columns, y for dependent columns. That's target here. Size, that's again the thing that we discussed earlier. Random state. Now here we also mentioned that stratify is equal to y. So basically y contains our target column, and in target columns we have some one categories and some zero categories. So basically stratifying basically means we need same proportion in all the sets. So basically why we do that? like we are trying to predict 0 and 1, and if everyone in our data set is in training set and we don't have anyone in testing set, that this will be a problem because model is only trained for the values where we have heart disease. That's why we want to make sure that we have same proportion. Again, standard scalar and fit transform to scale the columns. We scaled the columns, we created the new data frame and give it a name extend scaled and extend scaled. Now, why do we do that? Because we have such a big values and we have such a small values. We don't want to overshadow these small columns because of these lengthy values. That's why we scale them. Now, this is the main code for logistic regression. In this code, what we are doing here is we are implementing logistic regression function, and we are using random state max iteration. We can increase the iterations, but more iteration doesn't always mean that it's going to be better results. There is a time in training that we might need only 500 iteration instead of 1000. So it has no standard value here, but we can play around with it. Now, solver in logistic regression from sklearn, we have different solvers that can be used to train it, but we use most of the time we use linear here. Now we train it based on extend scale and y train values. Y train are basically our 0 and 1s, and we don't scale our dependent variable. That's why
What happened in the training model? Let's say.
Yes, let me explain. So first of all, let's start from very basics. What basically we are trying to train, right? When we said we are training a model, basically means we are trying to find the optimum values like beta naught, beta 1. Why? Because this will help us to fit the model. And now the second question that is, how do we get to the optimum values? So basically we train logistic regression based on the maximum likelihood estimation. We have this function, this one, likelihood function we call it. And in this function, what we do, we have yi basically means our target variables, ti basically means probability of observations. Okay. And what we do is we put values here, and this function helps us to find the optimum beta naught and beta 1. Again, like we in linear regression, we discussed thing called gradient descent. So basically we get the beta naught and beta 1 from here, and then we use gradient descent to get the optimum beta naught and beta 1 values. So this is basically mathematics that goes behind, and we don't deal with it directly, but in the back end of sklearn, this is what actually happening. Do you understand?
Yeah.
I think we discussed here. We discussed that earlier, right? In the previous session on linear regression.
Yeah, yeah.
So basically what we do is we get beta naught, beta 1, beta 2. We need to have the best values for these. Okay, and based on that, we fit the line in both linear regression and logistic regression. No, that's the algorithm. In gradient descent, we used in linear regression, we used MSA. MSC is basically mean square error, and we optimized that. Okay, we used random W naught, W1, or beta naught, beta 1 at first, and then we optimized that with this formula. Got it? But in logistic regression, we use maximum likelihood function. So basically, these are different. These are two same things for different purposes.
Okay.
So when we are trying, we say we train a model, basically means we get the optimum, the best beta naught and beta 1 values. Got it? Okay, now in logistic regression model, since we are dealing with a problem like 0 and 1, so what does that mean? That we need higher accuracy or something like that? So let's talk about that. Okay, whenever we are talking about classification problem, we're basically going to meet with something called confusion matrix. Now, a confusion matrix is basically a matrix that represent that how much values were correctly classified and how much values were not correct, not classified correctly. So let's talk about that. Now we have zeros and one, right? And we might get some good, some right predictions and some wrong predictions. Let's use this example to understand. Now we have 30 different data points, right? And that's what the confusion matrix will look like. So we will have Tn, Fp, Tp. So Tn basically means true negative, like it was zero actually, and we predicted it also zero, right?
Mhm.
And this is Fp, basically false positive. Basically, it was negative, but we predicted it as a positive.
Okay.
And so basically whatever goes on this section block and this block are correctly classified, and these two are wrongly classified. Okay, so whenever we create a confusion matrix, we will have a block of 4 values: true negative, false positive, false negative, false positive. And for the true positive basically means yes, they have a disease and we also predicted it as a disease. Okay, and TN basic true negative basically mean they don't have a disease and we predicted correctly. But if we have a false positive, it means we incorrectly predicted them as a disease, but they don't have any disease, right? So basically, these rows represent negative 0 and 1 for actual, the what the data have, right? And these 0 and 1 represent the predicted. So that's why we are getting like true negative and false positive. Do you understand?
Yes.
Now we have this data set. They actually have zeros and ones. And so basically, if we are trying to predict something here, for example, we are trying to predict this particular entry. Now this is actually a 1 value, right? So this is actually a positive value. But if we predict negative, we predict that it's a 0, it will go to this block. And if we predict it's correctly that it's 1, then it will go to this block. So in that sense, we get these blocks filled, and based on that, we calculate accuracy and different matrices. Now, for the accuracy and stuff, we have different matrices here: accuracy, precision, recall, specificity, F1 score, and ROC. Now, let's talk about accuracy first. Accuracy means from all the predictions, how much we made correct. Like we just take this one plus this one and we divide it with all the actual values, like all total values.
Okay.
Okay.
I understand.
Yeah, and it represents the overall accuracy of the model. But we have precision where we only want to know that how much positive prediction we made correctly. Okay, so basically when we have a problem like where positive predictions are more important or more sensitive, we go with precision. In the same manner, we have recall. Now here we have TP plus FP, so basically means these two columns. Instead of discussing it like that, we need to discuss it with some kind of example. So let's talk about the precision. We are trying to detect a fraud detection. Okay, now false positive are costly because we want to minimize the type 1 type. So there was a very famous meme related to type 1 and type 2 error. Yeah, this one. So it's going to be funny, but still it makes easier to understand. Now type 1 error is kind of error that you cannot even expect, right? That's not even possible, right?
Okay.
And type 2 error is basically that is possible, that's still in, but still they made a mistake, right? Like in this
Okay.
particular meme is saying an old man that you are pregnant, that cannot be even possible, we cannot even think about that, but still a kind of mistake that machine learning models make. I think I wrote somewhere here related to type 1 and type 2 order, but still, no, sometimes positive information is more costly and sometimes negative are more costly. So let's talk about that. If we are talking about precision, if we want overall accuracy, we will go with the accuracy, right? Where the predicting positive, more positive or predicting more negative doesn't make any difference. We just need overall good accuracy, we go with the accuracy. But if we are trying to minimize the type 1 error, or if we are more interested in the positive class, like in this example, we need this matrix to be highly correct. So we go with the precision. Okay, like we're trying to predict something like fraud detection, and we don't want to avoid it. It's okay if someone is not doing a fraud, but our system is detecting them as a fraud because it is not going to be cost much. But if someone is doing a fraud and our system is not detecting them, classifying it as a negative, that will have a higher impact and higher cost, right? So that's what we call minimizing type 1 error. So we are more concerned about the positive values. And if we are talking about recall, in recall, we don't want negative to be incorrect. Okay, like if we are representing false negative, like if someone is, let's go back to here, this one. Okay, so basically we're sensitive about these and we don't want to negatively classify something. So that's why it's called type 2 errors. Okay, and its recall is mostly related to medical diagnosis, and because if you're trying to predict some disease and you're missing it, basically you are going to go through all the wrong treatment, and that's kind of problem. So what it basically depends on you either go with good quality of accuracy, or you go with good quality of only precision, or good quality of only recall, based on the different problems. And now they move all along. Like if we go to this example and we find the best model, basically finding the best model or training the best model means the best beta naught and beta 1 values. Okay, now here we are having 96.96 percentage accuracy, but precision is 92 and recall is 100. Now if we are trying to predict something, like if recall is more important or we are trying to avoid type 2 error, we basically need to increase that, and we will modify our threshold, and we will see that how much we can go with. So basically, in you can play along with the threshold values and other values to get the better accuracy or precision and recall. That's totally up to you. Okay, and it basically the demand of problem that what we are trying to solve here. Do you have any question? If you have any question, any kind of confusion, please feel free to ask. Now, again, this is going to be very, very simple. We choose the model, we fit it on our training and testing data set. Once we have the trained model, we will generate the predictions on the training set and on the test set, right? And it will basically tell us about the training accuracy and testing accuracy. Like if we train a model, we are training a model, we are basically giving it some data, right? And when the model have a data, its accuracy is much higher than the testing data set. So we use both of them to see that how our model training is going. Again, we train the model, we get the predictions, we get the predicted probabilities, probability of each class, and now let's see. And we can also extract the coefficient from the model as well. Like here we train the model with the name lr.model, and we can use lr.model dot coefficient to basically get the coefficient values. X dot columns basically gives us the names of the columns that we're using. So basically we're trying to create this simple data set that gives us about the feature, their coefficient value and absolute coefficient value. And in evaluation, we go with accuracy, precision, and recall that we already discussed. Now let's talk about, okay, now we created the model, right? We have a confusion matrix. We have all kind of scientific terms that we want to that we are interested in. But the thing is, how can a non-technical person, a person that don't know about programming, can benefit from this, right? Like the end goal is to facilitate the common man. Now to do what we need to do here is we need to save our model, and we will package our model, like we will create a file that contains this model, right? There is a package in Python called joblib. So what basically it does, it dumps the model into .pkl file. So we basically .pkl file contains different kind of Python functions, and it also contains different kind of models that you have created. Like in Python, we created lr.model logistic regression that we just created, right? Now what we're trying to do is we are creating a file, heart disease logistic model.pkl, and we are dumping our model in this file, right? So we are saving our model in this particular file, and we are saving our scalar in this file, a new file like heart disease scalar.pkl, and a new file with the feature names. We are saving a feature names.pkl. So we're basically creating different files here. Now, why do we create that? Because we can, if we want to use this particular model, and if we want to show this model to someone, what we need to do is we need to create some kind of little application or user interface where a common man can use it, right? So what we are going to do is we are going to package our model, package our scalar, package our feature names, and we will use them in a little application. Also, we are going to save all the metadata as well in the PKL file. Okay. Now, once you run these lines of code, all this, you will see that you will get these files, feature names.pkl, heart disease.pkl. You can download them and you can use them. Now, how we can use them for a common person, right? Let's talk about that. Do you know about Streamlit? In Python, we have a package called Streamlit. I'm not going to explain all that right now, but we will have a proper session on Streamlit, right? Where we will see that how we can use Streamlit for different kind of applications. Now, in Streamlit, what we can do is we can use our models and we can create applications based on that, right? This is, we say, import Streamlit as ST. Basically, we are importing our package. We are setting the configuration, our application, that how it should look like, our icon, our application name, layout. And in this application, we are going to use this, our PKL, our model, our scalar, our feature names and all that, right? Basically, it will give a proper UI, or it will basically give a life to our model. If we want to run our application, we will just write Streamlit run, the name of the file that we just wrote in Python. Okay. If we run this, we will get something like this. Now, basically, what is this? We basically give a UI, a place where a common man can use our model. Okay. Now, if you are someone that don't know about programming or anything, you can just create a similar looking application and just share a link to them and they can use that. Like, for example, I'm a common man, I don't know about programming and I want to get a prediction. I came to you, created this app, and you shared a link with me. Now I will go to the application, I will select my age, I will select if I have a chest pain or not, or what kind of chest pain I have, my gender, my different blood pressure, sugar levels, and different kind of things. Okay, I will select them and I will click predictions. Now it's showing that there are 62.8% chances that I might have a heart disease. So basically what we did is we start from this raw data in Excel file. We used it to create a model that can actually predict either someone is going to get a heart disease or not. We saved our model, we give it a proper application format, and we create an application out of it. Do you have any question? And is it cool? Okay.